Hello, everyone. Welcome to the CPE 517 WS Digital and Computer System Architecture Lecture 2, Part 2. I'm Daslo. Okay, so I'm Professor Hang Liu. When we talk about parallelism and performance, we say how to measure the performance is very important, right? Typically, we use latency or time consumption or throughput to measure the performance. Well, the speed up of X relative to Y is the reverse of the execution time. Basically, if X spend execution time X and Y spend execution time Y, then the performance of X is 1 over execution time X, right? And Y is 1 over execution Y. So that's why you have the speed up of X relative to Y is the reverse of execution time Y over execution time X. Execution time. Execution time is the all clock time, include all the system overheads. CPU time only includes the computation time. So to measure the performance, we have this metrics, we have the speed up, we have the execution time, and then what do we measure, right? We use benchmarks. The benchmarks are the commonly recognized benchmarks, like both you and me and what the industry recognize. This is important. For instance, AMD said it's doing better than Intel, or Intel said it's doing better than AMD. How? How can they say who is better? Well, semiconductor technology is one thing, like I'm going to 3 nanometer, you are going to like 1 nanometer, etc. The real thing is the benchmark. Like for the same benchmark, you run faster or I run faster. That's why I'm saying I'm faster than you, right? So what are the benchmarks? The commonly recognized benchmarks like kernels, like some linear algebra, ones that used for ranking supercomputers of the world, or some toy programs that's very useful applications like sorting, like solving linear equations. Synthetic benchmarks like a Dresden simulation, or benchmark weights like SPEC or TPC-C for database, right? How do we define performance? It depends upon what is important to whom, right? For instance, if you're purchasing a computer and you care more about latency, like we discussed in last lecture, we said that you want to figure out what the application that really cares about latency. For instance, the real-time systems, like driver, or sorry, the brake system, right? So when I push the pedal, then it has the limited time to respond. If it goes beyond that time, it's not real time, and then it's a failure. And that's a single event. We don't care about throughput. We care about the single event's time consumption, okay? Well, so computer systems, like the drivers or driverless car, they care more about response time. And computer center manager, like I see a lot of applications ongoing, then I care more about throughput. For instance, in Holland Tunnel, we care how many cars passed through the Holland Tunnel in probably 1 day, right? Well, for a single driver like you only care about the time you spend during the passing the Holland Tunnel. That's the two cases. One is the computer system. The other is the computer center manager. Okay, I hope that makes sense. Then, if you still remember the first lecture, we mentioned Amdahl's law determines the single process performance. So what does Amdahl's law mean? It means like focus on the common cases, okay? Let me do a little bit of annotation. So let's see, for a program, you have X and Y. And I assume this is a ratio, okay? It's the wall belongs to 0 to 1. Similarly for y, okay? Then my assumption is that x plus y equals 1, okay? That means the total execution time is x% and y%. Total of them is 1%, 100%, or together is 1 total execution. And then I assume x is parallelizable, okay? And y is restricted to single thread, okay? So in that case, if I put in a lot of processors, right, in this test, then I can only improve x, right? Because a lot of processors means we are trying to use parallelism to improve, and I'm saying x is the only like a ratio that can be parallelizable. Okay, so foreseeing that, okay, it means x is the fraction that can be enhanced, right? And then this is x. Speed up is how many cores you have. Assume you have 2 cores, then your speed up is 2. So we see the new execution time is the 1 over 1 subtract x. That is y, which cannot be enhanced, plus the x, the new x, right? So it's x over the speed up. Okay. This is the principle of the Amadeus law. It actually tells us that we should focus on improving those fractions that can be improved, right? For instance, if you have a program, the fraction that can be enhanced is only 1%. No matter how many cores you use, you're gonna definitely suffer from like a very little limited performance improvement, right? So it's useless to put so many resources on this 1% of program. Well, on the contrary, if you have the program that has, let's say 99.99% is like embarrassingly parallelizable. So that actually means you should invest a lot of resource to do that, because by doing this parallelism, you improve the performance a lot. Okay, I believe that makes sense. So then the speed up is also very simple. It's basically, let me clean my screen. Okay. Still here. Okay. Still here. So 1 over the 1 is the original like time, and then 1 minus the fraction of enhanced plus the fraction of enhanced over speed up is the current time consumption. So if you still remember we have the speed up of reverse, right? So X over Y is the execution time of Y over execution time of X. So taking them together, so the speed up is the old execution time over the new execution time, right? So this is essentially the very, very important Amadeus law of computer architecture. It tells us that we need to take advantage of parallelism, but we have to focus on how many of them can be parallelizable. The parallelism can happen in a lot of places, such as multiprocessors, disks, memory banks, pipelining, multi-function units, like we have multi-core, right? We have RAID, an array of redundant disks, and memory banks, okay? Like we have 1 DIMM, 2 DIMM, 3 DIMM, or more DIMMs. And pipelining, so we have so many executions that can be executed in a stage-wise parallelism, right? Okay, and the principle of the locality is when we have so many cores, disks, memory banks, pipelining, and multi-function units, we want to reuse the data, right? Reuse the instruction. Why? Because getting this instruction and data ready takes time. Okay. So here in this Amadeus law, we focus on the common case, that the case that can be parallelized the most. Or we put it this way, we should focus on that component that takes majority of your time, right? So if you focus on the fraction that is enhanced is the majority of your time, that's the common case. So if you spend a majority of your time on the fraction enhanced, well, that fraction enhanced is like minority of your time, that's not a common case. If that's not a common case, no matter how many resources you spend on, you're wasting of your resource, okay? So taking them together, Amadeus law tells us we should focus on the most important part and invest the most resources. And that most important part should be parallelizable. If it is not, we have to rewrite the algorithm, we redesign the implementation, or even reinvent hardware. That's pretty much what my research focused upon. Okay, so since Amadeus law is very important, how important it is, it will definitely appear in your homework, in your midterm, in your finals, even during your interview. So definitely we're gonna have to do a very serious exercise for this problem. So for this problem, we suppose that we want to enhance the processor used for web serving. The new processor is 10 times faster on computation in the web serving application than the old processor. Assuming that the original processor is busy with computation 40% of the total time and is waiting for I/O 60% of the time. What is the overall speed up gained by incorporating the enhancements? Okay. So please use Amadeus law and 15 minutes to solve this problem. Okay. All right.